Good afternoon, everyone. So today in this session, we'll be discussing PYQs of hydrogen atom. We'll be discussing the questions related to hydrogen atom asked in your previous year NEET exam, right? So this will be the session for the NEET 2024, and we'll be starting with some of the questions of hydrogen atom, right? So let's straight away begin with the question number one. So question number one you can see on the screen is that the ground state energy of hydrogen atom is given as minus 13.6 electron. The energy needed to ionize hydrogen atom from its second excited state will be, right? And we know that, okay, we know that there are different infinite number of states or excited states for any atom, be it hydrogen atom or any other atom, right? So let's suppose uh, this is one of the state, this is the ground state, n is equal to 1 for the hydrogen atom. This is the ground state. So this is the state of least energy or minimum energy, right? And then we have second state, we have third state, and we have fourth state, right? As the value of n or the principal quantum number increases, the energy states come closer and closer to each other, right? Or we can say the energy gap of the energy difference between the two consecutive energy states decrease with increasing n value, right? So you can see here n is equal to 1, we call it as ground state, right? This is nothing, this is the ground state. And these n values goes up to infinity, right? They go up to infinity. And at infinity, we know energy of an electron is nothing, that's equal to 0, right? The energy of the electron is 0 at infinity, right? So n is equal to 1 is the ground state, right? And the energy of this particle at this state, in this state will be the ground state energy, that's minus 13.6 electron volt, right? And we know that the total energy of an electron in any excited state, right? In any state is actually total energy is nothing, that's equal to minus 13.6, right? Into n square upon z square, right? Into z square upon n square. Z square upon n square, right? For hydrogen atom here, Z will be equal to 1, right? Z will be equal to 1. We have the total energy as minus 13.6 into 1 by n square in the units of electron volts, right? In the units of electron volt. Now the question is that the energy need to ionize hydrogen atom from its second excited state. So ground state is n equal to 1, right? And the first excited state is nothing, that's n equal to 2. We call it as first excited state. First excited state. And n is equal to 3 is nothing, it's the second excited state. Second excited state. So for let's suppose fourth excited state, n will be 5, right? For fifth excited state, n will be equal to 6, right? So we have to actually find the energy needed to ionize hydrogen atom from its second excited state. Let's first of all try to calculate the energy in the second excited state, and that will be n equal to 3. It will be minus 13.6 upon 9, right? So it will be equal to, okay, it will be minus 1.51, right, electron volt. So this much will be the energy of the electron in the second excited state. This is the energy of the electron in the second excited state. If this much is the energy of this electron in the second excited state, it means that we have to supply this much of energy uh, to the electron so as this electron will make a transition from the second excited state to infinity, right? Second excited state to infinity, right? So this much energy is required, right? So the energy required is nothing. If we supply an energy of 1 point plus 1.51 electron volts to this electron, right? Then this electron will jump from the second excited state to infinity, right? Or we can say that we have ionized the hydrogen atom, right? The hydrogen atom will be actually ionized, right? From the second excited state. The energy required will be plus 1.51 electron volts, right? Let's move on to the question number second. The question number second is the wavelength of Lyman series of hydrogen atom appears in, right? So there are in a hydrogen spectrum there are different regions, right? There are different series of wavelength where Lyman, Balmer, Paschen, and Beckett phone series, right? So these are all the different series of series of a particular wavelength range, right? That are emitted in hydrogen atom spectrum, right? In the same way, for n equal to for the series where the transition takes place from any n to n equal to 1, right? That series we call as Lyman series, right? And the wavelength of Lyman series actually lies in the ultraviolet region, right? It lies in the UV region, right? The wavelength of the Lyman series actually falls in the UV region of the spectrum, right? It falls in the UV region of the spectrum for the Lyman series, right? So, which series falls in which region, which series will fall in the visible region, right? We have Balmer series, right? Which series will fall in the infrared? Which series will fall in the far infrared? All these things we need to remember, right? All these things has to be remembered because these questions are very frequently asked in your NEET exam, right? Lyman series falls in the visible region, ultraviolet region, UV region, and the visible in the visible region we have the Balmer series, right? So on and so forth, right? And now let's talk about the question number three. The angular momentum of an electron moving in an orbit of hydrogen atom is 1.5 h upon pi. The energy in the same orbit is nearly, right? So there is an electron in one of the orbits of the hydrogen atom, and in that orbit, the angular momentum of that electron is given as 1.5 h upon pi. And in the same orbit, we have to calculate the total energy of the electron, right? Now, first of all, let's try to find what is the value of the in which orbit actually the electron is moving, right? In an hydrogen atom, right? It's given that the angular momentum L is given as 1.5 h upon pi, right? And we know that according to Bohr's model of hydrogen atom, that total angular momentum of electron in any orbit is actually integral multiplier of h upon 2 pi, right? It's integral multiplier of h upon 2 pi, right? And the total angular momentum in any nth orbit will be nothing, it will be nh upon 2 pi. So only these angular momentums are allowed for an electron in any orbit, or we can say the angular momentum here is a quantized quantity, right? Only discrete values of the angular momentum are possible for the electron in an hydrogen atom, right? So now you can see here, let's compare the two equations here. We can write it as 3h upon 2 pi, right? That will be equal to nh upon 2 pi, right? So from here we can see clearly that n comes out to be equal to 3, right? So it means that the 1.5 h upon pi, this much of angular momentum will be present for the electron in n equal to 3, right? In n equal to 3. And the energy in that n equal to 3 is nothing. We know the total energy is minus 13.6 for the hydrogen atom divided by n square, this much of electron volts, right? So what we can do here, we put the value of n equal to 3 here, right? It will be 1 upon 9, right? So it will come out to be equal to 1.5 electron volts, right? So this much of energy will be present in the orbit, in the same orbit, right? For the electron which has the angular momentum equal to 1.5 h upon pi, right? So from this equation, what we did actually, we calculate the value of n, and from value of n, we calculate the total energy of the electron in that orbit, right? Now let's move on to the question number 4. Going on to the question number 4, in hydrogen spectrum, the shortest wavelength in the Balmer series is lambda. The shortest wavelength in the Beckett series is, right? So we know that according to Rydberg's formula, 1 upon lambda is nothing. It's r multiplied with z square, right? 1 upon n1 square minus 1 upon n2 square, right? So it means that, let's suppose if these are the excited states, right? These are the different excited states for an hydrogen atom, right? This is 1, this is 2, this is 3, this is n4, this is n5, right? So and for the Lyman series, right? For the Lyman Balmer series, right? For the Balmer series, right? The transition is between any N2 state, right? Any transition is between any N2 state to N is equal to 2, right? This is for the Balmer series, right? This is nothing. This is for the Balmer series, right? So this is nothing. This is for Balmer series. And if the transition takes place from N3 to N2, we call it as H alpha line. If it is between N4 to N2, it will call it as H beta line. Now let's look at this. Uh, we are talking about the shortest wavelengths, right? If we are talking about the shortest wavelength, it means that we are talking about the highest possible energy for the particular series, right? Highest possible energy. So highest possible energy for the bracket series will be nothing, or the Balmer series will be nothing. If an electron makes a transition from N2 equal to infinity, right? N2 equal to infinity to N1 equal to 2, right? So N2 has to be infinity, right? And N1 will be equal to 2. This will be for the shortest wavelength. Shortest wavelength. And similarly, N2 will be equal to 3 and N1 equal to 2. This will be for the longest Balmer wavelength. Because the energy gap between the, for a Balmer series, the energy gap between N3 and N2 will be the least, right? Will be the least. So it means that if the energy gap between N3 and N2 is least, the wavelength will be the longest, right? Wavelength will be the longest, right? In the same way, the shortest wavelength for the Balmer series is possible when N2 is equal to infinity and N1 is equal to 2, or we can say the electron makes a transition from infinity to first excited state, infinity to first excited state of the hydrogen atom, right? So that will be the shortest wavelength. So for the shortest wavelength, N2 will be equal to infinity and N1 will be equal to 2. So 1 upon lambda for the Balmer series, it will be Z is equal to 1 upon N1 square, right? N1 is equal to 2, it will be R upon 4, right? Or we can say lambda is nothing, it's 4 upon R, right? 4 upon R. This is for Balmer. I can write it as lambda p. And similarly, where to find the shortest wavelength in the bracket series, right? So for bracket series, we know that the transition will be from any excited state to n equal to 4, right? Well, Lyman, Balmer, Bastian, bracket, right? And full series, right? So these are the usually studied spectral series, right, for the hydrogen atom. And for the bracket series, right, for the bracket series, actually the transition takes place. For the bracket series, the transition will takes place any higher excited state, right, n equal to 4, any higher excited state to n equal to 4. This is for bracket series, right? And for the shortest wavelength, for the bracket series, if the transition takes place from the infinity to n equal to 4, right? The wavelength will be the shortest one, right? So once again, we can write for the bracket series 1 upon lambda as r times 1 upon 4 square, right? Or we can say lambda will be nothing, it will be 16 upon 4, right? 16 upon r, that will be the shortest wavelength for the Balmer series, right? Bracket series. Now let's talk. Okay, so it's given that 4 upon r is actually lambda, or we can say lambda will be nothing. Lambda will be actually equal to 4 times lambda b, right? 4 times lambda b. It will be 4 times lambda b, right? So the bracket series will have the shortest wavelength, actually 4 times the Balmer series, right? 4 times the Balmer series. So that's it. This is how we can solve this question, right? For the shortest and the longest wavelength as well. And for the longest wavelength of this bracket series, N2 has to be equal to 5, right? N2 has to be equal to 5 for the longest wavelength of bracket series, right? Now, talking about the question number 5, the radius of innermost orbit of hydrogen atom is given as 0.53 angstrom. What is the radius of the third allowed orbit of hydrogen atom, right? Uh, the radius of nth orbit of an hydrogen atom is nothing, it's 0.53 multiplied by n square, right? Multiplied by the n square. This is for the hydrogen atom, right? This is for the hydrogen atom. So we can say that for n equal to 1, we have the value for R naught, that's the proposed radius, right? That's 0.53 angstrom, right? And this is also in the units of angstroms, right? In the units of angstroms. Another question is that what is the radius of third allowed orbit of hydrogen atom? So for a third allowed orbit, n will be equal to 3, right? So R3 will be nothing, it will be equal to 9 multiplied by 0.53, right? That will be actually, it will be 4 point, okay, it will be 4 point, okay, 4.5 approximately, right? This much of angstroms, right? 4.5 angstroms approximately, right? So this much of angstroms will be the radius of the third orbit for the hydrogen atom, right? For the hydrogen atom. So this is the radius of third orbit, right? Now let's talk about the let T1 and T2 be the energy of the electron in the first and second excited states of hydrogen atom, respectively, according to the Bose model of atom. The ratio of T1 and T2 is, right? We know the total energy is nothing for the Bose model. It's actually inversely proportional to the n square, right? It's actually inversely proportional to the n square, or we can say that E1 upon E2, that we can write it as T1 upon T2 here in this case. That will be nothing. It will be N2 upon N1 whole square, right? N2 upon N1 whole square, right? So we're talking about the first excited state. T1 is the energy in the first excited state, or we can say that N1 will be equal to 2, and second excited state N2 will be equal to 3, right? So it will be 3 upon 2 whole square, right? That will be equal to 9 ratio 4, right? 9 ratio 4. So this will be the ratio between the two energies of the given excited states, right? Now moving on to the question number 7. For the question number 7, it mentions that for which one of the following atoms Bohr model is not valid, right? And we know that Bohr model is actually valid for the monoelectronic systems, right? For only those atoms which have only one electron in their orbits, right? So for monoelectronic systems, the Bohr's model is applicable, right? Like we have helium positive or lithium 2 positive, we have deuterium, right? We have hydrogen, right? So for all these atoms, they are valid, right? They are valid, but there is only one atom which is not a monoelectronic system, right? Neon is not a monoelectronic system, it's rather a multi-electronic system, right? So this will not be applicable for the option number 3, right? So for option number three, the hydrogen atom or Bohr's model of hydrogen atom is not actually applicable on a neon positive, right? Moving on to the question number 7. The total energy of an electron in an atom in an orbit is minus 3.4 electron volt, right? Its kinetic and potential energies are respectively, right? So we have to find the kinetic as well as potential energy for this electron. For this electron, the total energy is given as minus 3.4 electron volt. Remember one important relation between the kinetic energy and the total energy, right? The kinetic energy is nothing; it's always equal to negative times the total energy, right? It's always equal to the negative times the total energy, and the potential energy is always equal to 2 times the total energy, right? Is the relation between the two, right? And important point is that the total energy is nothing. That's actually equal to kinetic energy plus potential energy, right? So this is the relation, right? So these three relations has to be in mind with respect to the kinetic and the potential parts of the total energy of an electron in an hydrogen atom, right? Now it's given that the total energy is minus 3.4 electron volt. So the kinetic energy will be nothing. It will be plus 3.4 electron volts, right? And the potential energy will be nothing. That will be equal to minus 6.8 electron volts, right? So this will be the potential energy, right? So potential energy part will be, it will be 3.4 electron, kinetic energy will be 3.4 electron volts, and the potential energy will be minus 6.8 electron volts. So these are the two important relations with respect to the hydrogen atom, between the kinetic energy and the total energy, and between the potential energy and the total energy, right? So these are the important relations, right? And you can see here between the uh, kinetic energy and the potential energy, right? Kinetic energy and the potential energy. You can see here total energy will be nothing, that will be minus kinetic, right? Or we can say potential energy is nothing minus 2 times kinetic energy, right? Minus 2 times kinetic energy. So this is the relation between the kinetic energy and potential energy, right? So these are some of the relations which are which should be very handy to you for your exams, right? And questions are being asked on this equation as well, right? Let's move on to the question number 8. The question number 8 is the ratio of kinetic energy. This is once again the previous year question. The ratio of the kinetic energy to the total energy of an electron in an Bohr orbit of the hydrogen atom is, right? So what we have to do is that we know kinetic energy is nothing. It's actually minus times total energy, right? So the ratio of kinetic energy to the total energy is nothing. Uh, K ratio total energy, that will be nothing. It will be actually 1 ratio minus 1, right? And this was one of the options they are given, 1 ratio minus 1, right? So this was the correct option, right? 1 ratio minus 1 will be the correct option for that, right? So this is how we can find and similarly, if the relation between potential energy and total energy is given, is asked, that's the potential energy upon the total energy will be nothing. It will be 2 ratio 1, right? It will be 2 ratio 1. Potential energy upon the total energy ratio will be 2 ratio 1, right? Moving to the question number 9. The ratio of wavelengths of the last line of Balmer series and the last line of Lyman series is, right? So we're talking about the last line, right? The ratio of wavelengths of the last line of Balmer series and last line of Lyman series. For the last line here, the N2 value will be infinity. We know according to Rydberg's formula, 1 upon lambda is nothing, that is equal to R times 1 upon N1 square minus 1 upon N2 square, right? Multiplied by Z square, right? It's a very important factor. If an atom is different than the hydrogen atom, right? So for the hydrogen atom, we can have this Z value equal to 1, right? We can have this Z value equal to 1. So 1 upon lambda will be nothing. It will be R times for N2 equal to infinity, right? For the Balmer series, right? uh, N2 will be equal to infinity and N1 is 2, it will be 4. So lambda B will be nothing, it will be R 4 upon R. And similarly, we have for the Lyman series, N1 equal to 1, or we can say 1 lambda L will be nothing, it will be equal to 1, right? Uh, Rather, I can write it as R, right? Or we can say lambda L will be nothing, that will be equal to R. So the ratio we have to find, right, between Balmer and this. So lambda B upon lambda L will be nothing, right? So it will be actually lambda L will be 1 by R, right? So it will be lambda B upon lambda L will be 4 upon R upon 1 upon R, right? So this will be nothing, it will be equal to 4 ratio 1, right? Will be 4 ratio 1, right? 4 ratio 1 will be the ratio between the two, right? Now let's talk about the very important, once again, a very important last concept of this hydrogen atom spectrum, right? Hydrogen atom graph. So every aspect of hydrogen atom has been covered in this topic, right? In this session. So we'll be just touching the last aspect, that the speed of electron in an hydrogen atom, right? Consider third orbit of helium positive. Using non-relativistic approach, we'll assume that this electron be a non-relativistic electron, right? Otherwise, the mechanics of the electron will be a bit different, rather, but what we are doing here in the hydrogen atom at this level, right? We'll be assuming that it's a non-relativistic approach, right? So let's solve it by the non-relativistic approach, right? So consider third orbit of helium positive, right? Using non-relativistic approach, the speed of electron in this orbit will be given, right? K value has been given, Z value has been given, and Planck's constant has also been given, right? There are two ways to approach this question, actually, to calculate the speed of electron in different orbitals. The first way is you can just go by the by calculating the total energy, right? If you calculate the total energy here, total energy of this electron, we are talking about the third orbit, and the atom is helium atom, right? And we know that total energy is nothing, it's minus 13.6 multiplied by Z square by N square, right? For the helium atom, Z value is equal to actually 4, right? It's actually equal to 2 for the helium atom, and Z square will be 4. that's minus 13.6, 4 upon n square, right? The value of n is given as 3 here, so it will be 4 upon 9, right? So this much of electron volts will be the energy, right? So kinetic part from this energy will be nothing, it will be plus 13.6 multiplied by 4 upon 9 electron volts. So this much of energy will be the kinetic part, and this kinetic part will be nothing, it will be half mv square, right? Half mv square. So you can substitute the value of m here to calculate the speed of this electron in this orbit. So this is the method one, right? This is the method one, right? Apart from it, we have a generalized equation, right? Apart from it, we have a generalized equation, right? The generalized equation is actually, so actually the generalized equation is the speed of electron in any orbit is nothing. It's actually 2.18 into 10 to the power 6, right? 10 to the power 6 multiplied by z by n, right? Z upon n, right? Multiplied by z upon n, right? So here we have the helium atom, right? Helium atom, z value will be equal to 2, right? You can put the value of z equal to 2, it will be 2.18 into 10 to the power 6 multiplied by 2 divided by value of n, that will be 3. Accordingly, it will be 4.36 divided by 3, right? Multiplied by 10 to the power 6 in the units of meter per second, right? So it will be actually approximately it comes out to be 3.4, 1.4, right? 1.4 into 10 to the power 6 meter per second, right? So this much will be actually the speed of this electron, in n equal to 3, right? For the helium atom, right? So in general, the important equation is, this is the important equation, right? You need to remember this equation. It's a very important equation to calculate the speed of electron directly. For the non-relativistic approach, for any nth orbit, for any hydrogen-like atom, right? For any hydrogen-like atom. So this is the important equation to remember, right? So 2.18 into 10 to the power 6 z upon n meter per second. This much of speed will be the electron, for the electron in any nth orbit. You can just directly use this equation. If you remember this equation, you can save uh, around 1 minute of your time, right? To solve this question, right? Remembering this equation is recommended because in exams you cannot actually derive these equations, right? Or derive the results to calculate the answer, right? In 1 minute. So with this question here, we have actually touched, or we can say we have discussed each and every concept of the hydrogen atom, right? So in the next lecture, we'll be discussing with the nucleus, right? We'll be coming up with the nucleus and radioactivity part. That will be done in the next session. We'll stop here. Till then, take care and goodbye.